For decades, most advanced robots were basically just puppets. Their strings were being pulled by these massive data centers hundreds of miles away. Well, that's all changing. Today, we're diving into the tech that's finally cutting those strings and giving robots a mind of their own. We're talking about Edge AI. So just imagine a self-driving car for a second. It sees a kid run out into the street. Now, that visual data has to travel all the way to a server, get processed, and then a stop command has to be sent all the way back. That round trip, right, even if it's just a tiny fraction of a second, can be the difference between a near miss and a total tragedy. That delay, that's latency, and it's the fundamental, critical flaw of cloud-based robotics. And this really breaks down that massive shift perfectly. On the left, you've got the old way, a robot that's constantly phoning home, asking the cloud for permission to do anything. But on the right, you have the new way, a robot that can actually think for itself, right there on the spot. I mean, the difference is huge. It's the difference between a simple tool and a truly autonomous agent. 200 milliseconds. That's literally faster than you can blink. But in the world of robotics, believe me, that is an eternity. It's enough time for a high-speed industrial robot to make a catastrophic error. It's the kind of delay that could cause a surgical robot to make a fatal mistake. For real autonomy, the reaction time has to be instantaneous. 200 milliseconds? It's just not going to cut it. It's way too slow. Which brings us right to the solution. We've got to move that intelligence directly to the edge. We've got to put the brain right on the robot itself. So here's the key idea. An Edge AI agent, it's not just a robot following some pre-written code. No, it's an autonomous system that perceives, it reasons, and it acts all on its own hardware. No cloud connection is needed for those core critical functions. It's all self-contained. But it's not that easy. You can't just take a data center's worth of computing power and cram it onto a robot. That introduces some really tough physical limitations, what engineers call swap constraints: size, weight, and power. You just can't strap a massive power-hungry computer onto a small battery-operated drone, right? It would never get off the ground. So how in the world do you do it? How do you squeeze a supercomputer into a robot without weighing it down or completely draining the battery in 5 minutes? Well, the answer is in this beautiful harmony between hardware and software. The best way to think about it is like a specialized team. Instead of one person trying to do everything, you've got an expert for each specific task. The CPU, that's your general manager, handling all the day-to-day operations. The GPU is kind of like the visual artist, rendering all the complex graphics. And then you have the NPU, the neural processing unit. This is the genius mathematician of the group, and it just crunches those complex AI calculations with incredible speed and efficiency. But of course, the hardware is only half the battle. You've also got to shrink these massive AI models to actually fit, and that's where software optimization becomes absolutely critical. Things like quantization, that's kind of like translating a really complex novel into a simpler language the hardware can read way faster. Then there's pruning, which is like a good editor, just cutting out all the unnecessary words to make the model smaller and more efficient. And finally, you've got acceleration, which is like a custom-built engine fine-tuning the software to get every last drop of performance out of the hardware. And look at this. This is an amazing picture of how it all comes together. This is basically the blueprint for a modern robotic brain. You can see how all that sensory information from cameras, from LiDAR, it all flows into this central edge brain. And inside that brain, the information gets processed in two very, very different ways. Let's break that down because it's really cool. You can think of it as having two speeds of thought. You've got the fast path, which is for pure reflexes. We're talking microsecond reactions, like instantly dodging an obstacle. And then you have the slow path. This is for your higher level reasoning, planning out a complex task, like figuring out the best way to clean up a spill. And just so you know, this isn't science fiction. This is the actual tech being rolled out today. You've got these powerhouse chips like the NVIDIA Jetson, specialized AI accelerators, and these incredibly powerful foundation models like GR02. I mean, this is the trifecta that's making truly intelligent, autonomous robots a reality right now. Okay, so we've had a look inside the brain. Now let's see how this whole agent actually operates in the real world, how it connects all that internal logic to physical action. So it all comes down to this fundamental rhythm, this loop. A delivery drone sees a tree branch in its path. That's perceive. It instantly calculates a new route to avoid it. That's decide. And it adjusts its propellers to change course. That's act. And this loop is just running constantly, thousands and thousands of times every single second.
Which, of course, leads to the most important question of all. When something totally unexpected happens, in that one critical moment, is this loop really fast enough to keep things safe?
And the answer is a resounding yes, absolutely. Because that entire loop runs on the edge the moment an anomaly is detected. An obstacle, a person stepping out in front of it, the robot reacts instantly. It doesn't have to wait for permission from some distant server to hit the brakes. That potential dangerous latency spike from the cloud, it's completely avoided. Now this instant, local reaction time, it's not just about making individual robots safer or faster. It's actually the key that unlocks the entire next evolution of robotics, decentralized intelligence. I want you to picture a giant warehouse with hundreds of robots zipping around. With a centralized cloud system, that would be a recipe for total chaos. But with Edge AI, these robots talk to each other directly. They negotiate right of way, they avoid collisions, and they work together as this seamless, intelligent swarm. It's like this beautiful, chaotic dance, all choreographed in real time without any central controller. So, what's the big takeaway from all of this? Well, it really boils down to this one powerful idea. For robotics to take that next giant leap forward into our daily lives, its intelligence can't be living miles away in a data center. The future of robotics is right here, on the device, at the very edge of the network.